Hi everyone, welcome to part 5 of the Z80 computer series. This time I'm going to be looking at adding some RAM to the system. We've already added some ROM, so I'm going to be moving on to adding some RAM. But before I get into that, I want to show you what I've been working on here. You can see I've made a bit of progress. I've now completely eliminated the breadboard that was connected with a bunch of wires through here. Now everything is wired underneath. I won't show you that mess, but this is now running on its own without any additional board. It just requires power. I've got a choice. I can either use a barrel jack connection through here, or I've got some clip-on connections here for connecting to a bench power supply. So if I fire this up, we'll see what happens. Okay, that is what I was expecting. It's quite normal. I haven't really addressed the issue of power on reset, so we're not getting a clean reset when we power up. But if I hold down the reset button and then let it go, you should see it's running. It's running the normal program that we've been running in the previous videos, and hopefully you should notice it's a bit quicker now. Seems to be responding a little bit quicker. We could go even faster than this, but I want to keep it reasonably slow so we can keep track of what's happening. The way I've speeded it up, I simply swapped the capacitor, which is here, and that's the capacitor that was on our auto clock circuit. It was originally 10 microfarads. I just swapped it out for 4.7 microfarads. So if you think about that, it's a lower capacitance, so it's going to charge up quicker and it's going to lose its charge quicker because there's less capacitance there. So going from 10 microfarads to 4.7 microfarads roughly doubles the speed of the system here. You can see it's already got right through the program and it's now just outputting FF. You can see I've done quite a bit of work here since we last looked at it. I've now got all 16 address lines in here. I've got the 8 data LEDs, and I've got 6 control signals connected up to lights. We've got read, write, memory request, IO request, halt, and M1. There are a few other control signals that I could connect up eventually, like bus requests and interrupts and things, but I'm not going to get into that right now, so I didn't bother connecting those up. These things here are Resistor Networks. I'm mainly using these as current limiting resistors for these LEDs, but a few of them I am using for pull-up resistors on the CPU. And then I've also connected the clock circuit, and the manual clock and the auto clock circuits are here. This is our inverter chip that we're using for that. Reset button here and manual clock here. And then there's our clock selection, dip switches. So it all works as per the breadboard, and you can refer back to the original diagrams if you want to see the diagrams for this. I will eventually get around to putting the diagrams up on a GitHub page or something if you wanted to replicate this. I think that's about it. Oh, of course, the other work I did, I've actually got the Z80 on this board now, as well as the ROM. I think that was on the breadboard as well in the last video. So they're now both on here. So basically we've got everything that we've done so far is now on here. So I'm at a position now where I can add some RAM. I've got a socket here ready for the RAM, but I am going to prototype the RAM circuits up on a breadboard before I do that. So let's look at a circuit diagram, and we'll look at the overall memory configuration of this system. Okay, so here's a schematic. I'm going to be looking at the overall memory. So we've got both the RAM and the ROM here. This is probably the most simplest way you can connect memory to the Z80, the simplest configuration. As we know, the Z80 can access 64K of memory, or it can directly access 64K of memory. So the simplest way of configuring that is to just go with 32K of ROM and 32K of RAM. It's maybe not the most efficient way or the most desirable configuration, but it's the simplest. We really want to put the ROM in the bottom half of the memory address space, because when the system boots up, it will start executing from memory address 0. So we need to know that there is some instructions at memory address 0 and that we can guarantee what they are. If we configured it so that the RAM was at the bottom, we couldn't really guarantee what instructions would get executed when you boot up. So that's why we put the ROM in the bottom half. So this might look quite complicated, but once we start breaking it down, it's actually really quite simple. So I've got two chips here. These part numbers are the part numbers that I'm using. I believe they're the correct part numbers that I'm using. The AS6C62256 is a 32K RAM chip, and the AT28C256 is a 32K ROM chip. I'm not quite sure why EasyEDA is highlighting some of these connections in red. Just ignore that. There's clearly some problem with this particular design at the moment, but don't worry about that. It's not relevant. So each chip is connected to both the data bus we've got here and the address bus, which is this one going down this side. Now the data bus, we've got all 8 connections on the data bus, D0 through to D7, connected to both chips. So we've got D0 to D7 here as well. And now with the address bus, we only connect the first 15 address lines. So 16 address lines can address 64K of memory. So we only need 15 address lines to address 32K. So that's why there's only 15 lines here, A0 through to A14. It's the same on both chips, and that's because they're 32K chips. So all that leaves us, obviously we've got power and ground on both chips as well. So all that leaves us is a few enable lines on each chip here. You'll have to excuse my symbols. I've got different notations here. This one's using the exclamation mark and this one's using the hash symbol. And again, I'm using the exclamation mark over here. But either way, they represent active low connections. Either a hash or an exclamation mark represents active low. So we only have these 3 connections on each chip to sort out once we've sorted out the data and the address buses. So we'll start with the A15 line. Now when we're trying to access memory in the bottom half of the address space, the A15 line will be low. Doesn't matter which address we're accessing, as long as we're in the lower half, the lower 32K, then A15 will be low. So that means we can directly connect it to the chip select line of our ROM. So when we're trying to address memory in the bottom half, this chip will be active. Now for the upper half, we need to invert the signal. So when we're in the upper half, A15 will be high, so we need to invert it to make it low before we connect it to this chip. So A15 is really just selecting which chip we're addressing. So that's relatively simple. And then all we need to know after that is this a memory request? Because we might be accessing I/O, so we want to be sure that it is memory that we're trying to access. And also, is it a read or a write operation? So we've got the 3 signals here that will tell us that. We've got the memory request line, and then we've got the write line and the read line. And they're all active low. So this symbol here is an OR gate. Now if you don't know what an OR gate does, you can go and Google that, but very simply I'll explain. The way an OR gate works is its output is high when either of its 2 inputs are high. So if this input is high or this input is high, then we get high on the output. So it's an OR gate, so it's either or. Now the only way the output of an OR gate can go low is when both inputs are low. Because if you think about it, if either of them are high, we're going to get a high output. So they both have to be low to get low on the output. And that's actually quite convenient because it's exactly what we want. So when we have the memory request line low and the read line low, both of these inputs will be low, and therefore this signal here will be low. So we know when this goes low, we know that's a memory read request. So we connect this line to both of the output enables on the chips. That's actually pin 22 on both chips. An output is when we want to read from the device. It will output its data onto the data bus. And then we've got exactly the same up here. We've got another OR gate, but this time it's hooked up to the write line. So when memory request is low and write request is low, or write is low, then this line will go low, and we connect that up to the write enable. But this time we only connect it to the RAM chip. We don't ever want to be writing to the ROM chip, and I've got a little disconnect symbol there to indicate there's no connection made there. We never want to write to the ROM chip. I mean, in the past, ROM chips, you just couldn't write to them. They were read-only, as their name suggests. But modern ROM chips, we can actually write to them to program them. So we definitely don't want to accidentally be doing that and overwriting our program. So we want to make sure that we don't connect the write enable line on the ROM chip. But that's basically about it with the memory. We've just got a couple of OR gates and an inverter. The OR gates are controlling the type of operation we're trying to do. We're guaranteeing it's a memory request, and it's either a write or a read. And then the A15 line is just controlling which chip is actually active. When A15 is low, this one's active, and when A15 is high, it's inverted, and this one becomes active. And that's basically all there is. So what I'll do next is I'll get this built up on a breadboard. I've already got the ROM chip in my system, but the RAM chip and the logic gates I'll put on a breadboard. And now I will have to make some modifications to my system because I believe my ROM chip, we've got two lines here, output enable and chip select, and I believe I've got them directly hooked up to memory request and read. So I'll need to disconnect those so that we can route them through our logic chips. But I can directly connect A15 to this chip select on my circuit board, so I will do that because that will be permanent. But the rest I'll build up on the breadboard. So here's a new program for us to look at. This is going to be used to test our memory. Not our memory, the computer's memory. I'll go through this line by line, and what I've done as usual, I've written out the mnemonics here, which I'll go through, and then I've also hand compiled them and worked out all the hex code for all the instructions. So the first thing we've got is load HL, 8000 hex. Now I don't think we've looked at a 16-bit load before. So the HL register is a 16-bit register pair. So it's two 8-bit registers being used together to form a 16-bit register. Now the interesting thing with this, if you're compiling by hand, you need to know this stuff, is that if you look at the number 8000 that we're loading in here, or it's 8000 hex, 8000, you break that down into 2 bytes, so we've got 80 and 00. Now the 80 is the high value, which gets loaded into H, and the 00 is the low part of the number, which gets loaded into L. That's incidentally what H and L stand for, if you didn't know, high and low. But that happens kind of in... depends which way you're looking at it. I was going to say reverse order, but it happens with the low byte first, which is, so it's 00, the low byte needs to be loaded first and then the high byte. So that was one of the things I got wrong when I originally hand compiled this, and I put the 80 here and then the 00 here, which is wrong. It has to be the low order byte first and then the high order byte. Just an interesting little fact. Okay, next instruction. This is load HL, AA, but the HL is in brackets, so that means we're talking about an address. So what we're saying is load the address that's held in HL, or load into the address being pointed to by the HL register, and this is the value that we're going to load in. So we're loading AA into memory address 8000. Then we're going to inc HL, so that will now be 8001, and then we're going to load BB into address 8001. And then we're going to inc HL, and we're going to load CC into what will be address 8002. So AA is going into address 8000, BB is going into address 8001, and CC is going into address 8002. Now the reason I picked address 8000 is that's where our RAM starts. 8000 hex is the bottom of our RAM chip. So all of these addresses will be in RAM. So we've loaded the 3 bytes into RAM, and then what we're going to do next is read them back and output the values and check they are correct. So we're going to load HL with address 8000 again. So back to the beginning. I'm going to load the register B with the number 3. And the reason I'm doing that is because I've got this loop here, and if you look at the bottom, I'm using Djnz Loop. And if you remember that Djnz uses the B register as a counter, and when B gets down to 0, it will jump out of the loop and fall down here. So we're going to loop around this 3 times. That's why I've loaded the number 3 into the B register. Next thing I'm doing is loading what's in the memory address being pointed to by HL. So that's memory address 8000. I'm going to load that into register D. Then I'm loading register C with a 0 because that's our first output device. Device 0 or IO address 0. And then we're using out C, D. So we are writing out the value of register D, which is what we read back from the memory up here, and we're outputting it to IO address 0, which is our green LEDs. Then I'm going to inc C, and I'm going to out C, L, and inc C, and out C, H. So I'm just writing out the memory address, and I'm writing that out to our red LEDs, which are IO address 1 and IO address 2. Finally, I'm going to inc HL to move to the next memory address, and then we've got our Djnz, which is going to loop around and do the whole thing for the next memory address. It'll do that 3 times in total, and then finally it should drop out of the loop and go to halt. The reason I put the halt in there is just so we can test our halt light, because I haven't done that since I rebuilt the circuit board. So hopefully that's fairly straightforward. We're just loading 3 bytes into RAM with this top part of the program, and then we're reading them back and outputting them to our LEDs. So let's go back to the circuit board. So I've built the circuit up on a breadboard. It's a little messy here, so a little tricky to follow, but again, just refer to the circuit diagrams and you should be fine. Over the back here, I've got an inverter chip. This is a hex inverter. So there's 6 inverters on there. I'm only using 1 of them. And then in here we've got a quad OR gate. So there's 4 OR gates on there, and we're using 2 of them. And then buried in here is our RAM chip. I've got the program loaded onto the EEPROM. I used the TommyProm programmer as we did before, so the program is loaded in. I'm not going to pretend that this worked first time. I've run through this once already, and I had to do quite a bit of diagnostics to work out what was wrong, but I found a few wires here were swapped around. They weren't where I thought I had them, so I must get this labelled up. But anyway, let's fire it up and see what happens. Okay, let's give it a reset. I do really also need to solve this power on reset problem. So let's give it a reset. And there's the A at address 8000, the B at address 8001, and C at address 8002. So it is working. That was a little bit quick because we are running quite fast now. Let's just stop that for a second. So if you think about what our program was doing, we were writing to memory addresses 8000, 8001 and 8002, and we were writing the bytes AA, BB and CC. Nothing actually comes onto the display until we start reading back. So I'll just run through that one more time. Let's power up, give it a reset. So only when we start reading back do we see AA, BB and CC. Yeah, that's a little bit too quick for me to keep up with now, but it is working. We successfully wrote the 3 bytes to memory and we read them back and we got back what we expected. So I think the next thing for me is to transfer these circuits onto this board. Having RAM on the system is actually going to open up some more possibilities to us, because up until now we couldn't do things such as subroutine calls or use the stack. And the reason we can't use subroutine calls is because they require the stack. So I will probably go into that a little bit more next time, explaining what the stack is, why it needs RAM, and we'll look at some subroutine calls. So we can look at a few more different instructions, and we'll do that in the next video. So we'll leave this here. As always, thanks for watching. If you liked the video, give it a thumbs up. It's really important to me if you can do that. And if you haven't done so already, please subscribe to the channel. And I'll see you next time.